I'm starting the live stream, I think. Yeah, pretty sure this is on. Hello, welcome to Twitch. This is Hello Maths 222222, and good to see you. My chat is slightly broken because everything's hidden by this advert. It's an advert for Crunchyroll. How do I get rid of that? Right, there you go. Hello. That's how we start. Right, good. It's telling me that I can subscribe to me, and then I get some Crunchy rolls or something. I don't really understand. So maybe that's a thing for you as well. If you subscribe, which you really don't have to do, then perhaps Crunchy rolls appear. Goodness knows what that means. Hello, Mary. Good to see you. And shout out, I suppose, to Blue Molten Hops Beverage, who followed me on Twitch 2 hours ago, possibly getting ready for this. I always wonder how people find this when I'm not live. I mean, I wonder a bit how people find it when I am live, but there we go. I did a thing recently. I don't know what scale of thing this was, but I sent in an audio clip to a radio show. So I suppose like 1 in a million. If you're here from the John Richardson morning show on Saturday, Absolute Radio, where they had a call in from someone who had done some Skittles maths, then that's welcome to the Twitch show. What a weird way to find out about maths on the internet. Meme Machine Rex, you're taking the credit for luring Blue in, not me. Brilliant. Okay, good. In that case, forget all the John Richardson stuff. Right, good. Everyone's doing all right? I hope everyone's doing okay. Right, I am trying to studiously get on with understanding quadratic forms. Today's the day, I think. I say that every time, right? Today's the day. Maybe I will understand something about quadratic forms. We got some facts on the screen. I think I'm distracted though by also thinking about, well, there's quite a lot going on at the moment. Possibly I'm supposed to be thinking about other sorts of content, but no, I think I'll focus down on my quadratic forms. Good. I always like it when viewers know who each other are. That wasn't quite a sentence, was it? For each viewer, no. The happiness function is defined on the set of... No, never mind. Okay, never mind. Right, good. What on earth am I doing? Something about periodicity in a topograph. I cannot remember being on this page. But look, this previous page has got my annotation on, so I must have been at the thing before. Oh, yes, this was the fact about the discriminants being useful information. And with this kind of triangle inequality fact, it was good. Is this as far as we got? I think possibly we came back to this page. Possibly we came back. Yeah, both ways, nice. Okay. What do I want? I want the graph of connections among random viewers. I want the graph to be non-trivial. And the happiness is like the number of edges or something. That implies that I'm trying to organise some sort of edge create. Anyway, never mind. Yeah, all other major clusters, right? If we remove Meme Machine Rex, then we've got some strongly disconnected graph or something. We're at the scale where degrees of distance, right? You're either tuned into chill maths because you've seen me do a different thing, that's quite direct, or maybe because Meme Machine Rex told you to. It's got 2 degrees, possibly. Right. We don't have the most viewers, but we do have the best viewers. We're just not allowed to say that in chat because that's what the bots say, and you get timed out if you say best viewers in chat. Right, good. Okay. Right, some stuff about discriminants to tell us which sort of quadratic form we're looking at. There you go. Mary's worked it out. Herbs learn. Yep. You have to find other ways to describe how great you all are. It shouldn't be too hard. Right. Okay. We've got values of these things. This is pretty nice, I think. Has one integer solution and there's infinitely many integer solutions. Provided Q is hyperbolic. This is the periodicity thing. if you have a solution, then follow along the periodic separator line, find more, or parabolic. I can't really remember about parabolic ones, but I think around a parabolic one they're kind of all the same around the outside. So if you take a value, then you can choose any of those and branch off in any of the directions from your kind of, was it 0 on the middle? Does a parabolic one necessarily take 0? Yeah, because if you put 0 into these things, then you get 0. Oh, am I allowed to put in 0, 0? I've forgotten how this works. Ha! Brilliant. Welcome back. Oh. Parabolic felt like it had ways to get at 0. Oh, let's go and look back right at the definition again. I know it's bad to go back too much, but here we are. Marvellous audience is excellent. The observers is too spooky. I'm going back to the start of section 5. I'm sorry. I just want to think about parabolic again. Parabolic ones do take the value of 0. The only ones I could think of took the value of 0, so I'm glad that is the thing. You haven't got ones where the minimum is sort of 3 or something. Yeah, we thought about being near the 0. Around the 0, you have this thing going on around the 0, and you get, what was this down here on the right? Things are equal, so that it doesn't go negative. It pretty much means positive everywhere. Good, right, okay, so single signed parabolic ones. 0, and things around. Okay. I'm supposed to think about elliptic forms, which do. No, I'm confused. I'll be alright, I think, but only positive values or only negative values. Can I have an example of that one? I'm a bit confused. What on earth is this? Right, so 2x squared plus 3y squared, we're not imagining putting in 0, 0. So other than that, there could be some minimum value. Yeah, I've confused myself by wondering whether or not we're allowed to plug in x equals 0 and y equals 0, which would of course always give 0 in all of these quadratic forms. I think that's not allowed. Let's reread the top bit. Yes, always assume that xy is not 0, 0. There you go. I've successfully worked my way backwards to almost the first sentence of the section by forgetting things and thinking, oh, I'm sure that came up before. It's okay, backwards and backwards and backwards. Who told that story? There's a story about trying to understand a maths book. You want to understand maths, so you get a maths book and you look at the back to find out what's going on at the end, and you think, right, none of this makes any sense at all. You turn back a page, find out what's going on, and you end up at the start. Yes, sometimes we're interested in plugging in co-prime numbers, and sometimes we're interested in just plugging in any pair of numbers. Yeah. If you're interested in the values that you can take, you only have to think about what happens when you plug in co-prime numbers, modulo then multiply up by squares. That's somewhere down the end of this page. Spatial awareness, don't let me down now. No, spatial awareness may have let me down now. Somewhere down the bottom of one of the pages. If you're interested in the values it takes, then you only really need to think about the values it takes on co-prime pairs of x and y. Because then if you then think about ones where they have a common factor, well, that's which is going to be common factor squared times the value it was taking on the co-prime parts of the numbers. What's that called? If x and y share a factor, and I want a word for x over d and y over d, the kind of co-prime parts of the numbers. Not that it's d. Oh, I suppose then. Oh dear. Yeah. So what would that be? The highest common factor of x and y is d. I should not use that notation because we use that for coordinates, don't we? So the highest common factor of d, then the highest common factor of x over d, y over d is 1. I would like a name for these things. Co-prime parts? Let's just call them highest uncommon divisor. That's excellent. The story could have been me. You're right. Standing on the shoulders of giants. Right, okay. I'm going to try and get back to page 121, where I was a second ago. Or something like that. Around here, wasn't it? How many solutions do you get? And I'm going to push forwards, I think. we thought about equivalent forms about a month ago, about their values, and that being enough to identify things because of rules like this, where if you give me the three values a, b, c around a point, you can work out not the quadratic form, but you can work out the, what are we calling this? Discriminant of the quadratic form. In terms of those values a, b, and c, it is sum of the squares minus twice the sum of the pairs, which is a bit better. Hello. Oh, thanks for this. Who's this? This is Mortal. Oh, wait, hang on. That's a string. Let's go for the space after the first L. I think that's Mortal Louis. Hello, thanks for the follow. Good to see you. I think I plugged the audio in correctly, so you might have even got the audio notification through the stream. Wow. Crikey. Mean Machine Rex has invited me to something called an Element Math Collective. I don't know what that is. I'm going to have to look that up after the stream. I'm actually not super. I'm becoming level. I'm not sure how keen I am on Discord right now. We'll have a think. That's a very strange thing to say, isn't it? Thanks for the invite. I'll think about it. And partly I'm thinking about Discord. Nice. Right, there you go. That sounds mysterious, doesn't it? Great. I do like the idea of notifications. I stream very regularly, but regular but irregular, which is weird. Always at the same time. Not every week. Although I have an announcement about that, I think, as well. If I change stream time, either earlier in the day or later in the day, I think I would go later in the day. I'm thinking about moving the stream time to 4 o'clock, or possibly, sucks in, 10 a.m. I don't really think 10 a.m. is going to be popular, is it? Oh, can we do a poll or something? Can we do a poll? Poll, create new poll. Stream time, preference. There are going to be two options. They're going to be like this. I think 4 p.m. is going to win, but we'll find out. And so the poll is stream time preference. Does it show up there? Not earlier. Yeah, okay, you get to vote. 3 people have kind of already voted by typing in chat, so there you go. Oh, Herb gets free breakfast. Oh, right, okay. I'll never get between someone and free breakfast. I'm possibly going to have a new regular commitment that overlaps with 2 p.m. on Sunday. Which it's a bit of a shame because I've been going on 2 p.m. on Sunday for ages. Right, okay, we'll do some voting. There we go. Only at 10 a.m. Right, well, okay, there we go. What am I doing? Oh yes, we were thinking about these. We got really stuck on these. I think this is the furthest we've ever got with this. Within a cycle was a phrase that we didn't understand. And this is important if we want to do this classification, because then we're going to get onto things like the class number, which I would quite like to understand. But I've got a feeling I need to understand the things before. Oh, did that finish? It's 100% 4 p.m. Cool, that's quite interesting. Thank you. I sort of hope I don't bias anyone by before the vote expressing my preference, but there we go. We did it. We voted. It's probably going to be 4 o'clock. Check Twitch. Twitch has got a thing like a schedule, and that's also the place where I tell people if I need to cancel one. The schedule's quite boring because I only stream once a week, but that's where you can find out when the next one is. That's a message to the future. If you're somehow watching this on YouTube or something, you're thinking, well, he's changed the time. What on earth is he up to? What's he doing now? Then you can check the Twitch schedule. I'm sort of new here, although not really new here, but I don't think I'm ever going to work it out. So I'm going to carry on pretending to be new here. Right, here we go. We've got possibilities for the values of discriminants. I liked those calculations. There were some tricks that bounded the value of h, which is something like the difference in the arithmetic progression that you find when you look at values across a kind of double Y-shaped junction in the topograph of the Fairy diagram. We get long sentences here. We get long sentences. If you like a long sentence, it's chill maths. So what do we do? Love democracy. Right. Yeah, okay. Well, hang on, so what's going on here then? One might wonder what would happen if we continue to take a larger value of h that don't do that. I mean, you're not going to find any because we proved that they have to do that. H is 10, we would have AC is 90. So this would have to be 9 or less, which is why we did it. Large values of h run into similar difficulties, that's why, yeah, okay, good. That's why we did it. Okay, good, right, come back again then. Okay, so this is the cycles section, which is the thing I would like to understand today, I think. Yeah, right. I switched off points voting for that one. I thought, although maybe that was, I thought this is the thing where you want, like, count the viewers one each rather than counting the viewers 1 point each. Although, yeah, arguments both ways, depending on points. Right, anyway, I still find it really funny that Twitch has a democracy option. It has this poll thing, but you can bribe the polls using points, which have no monetary value, so it's not quite bribery. But you can vote. This like tick box option for like, would you like people to spend to vote more? It's a weird concept. Yeah, so I think Mary and Maths 2222222 are roughly equal on points accumulated. Not a stat I actually have access to. Ooh, maybe I do. That's a good question. So can I find out that sort of thing? Ooh, let's not. Manage power-ups and points. Can I find out facts about points? That'd be good, wouldn't it? Oh no, I just set up community challenges and things. Okay, anyway, probably equal on points accumulated, but then points spent. Oh, I've got another advert for Crunchyroll. Why am I getting adverts? It's my stream. I'm currently streaming Twitch. Like on the control panel where I have controls for the stream, it's currently advertising the idea that I can subscribe and also get Crunchyroll. Right. Okay, we're going to read about cycles of hyperbolic forms. This is a very serious stream. We've got serious maths to do. Hyperbolic forms. Are hyperbolic forms my favourite? They're all right. I kind of like the elliptic ones as well. So the hyperbolic ones are the ones like this, which then I think, ooh, could give me approximations of root 2. And the elliptic ones are the ones like this, where I think, ooh, could be a fun expression for something to do with Gaussian primes, sum of two squares, like a weird. Factorise this over the complex numbers. Ooh, right. The topographical hyperbolic form has a separator line. So for each edge in the separator line, we have the edge label H, the adjacent regions labelled P and minus Q for P greater than 0 and Q greater than 0. We can assume H is positive or 0 by reorienting. Are we looking at a particular edge? I can never remember if H is some sort of constant. I don't think it is. I don't think it is. Or along the separator line? No, I don't think so. The discriminant is constant everywhere. But, yeah, okay, we have this. Since P and Q are positive, this applies H credits at most delta. So we've seen this sort of thing before, this about the periodic thing. Finitely many possibilities for H. Okay, that's my vague memory, it's not constant. Along the separator lines of forms of the given, right, okay, so along all possible hyperbolic forms with a given discriminant, so any finitely many possible possibilities of H, is that going to tell me then, if I know H, I can work H, we can work out, diagrams like this, didn't we, with lines going above and up and below, tree things growing above and below the separator line. If I know H, is that going to let me work stuff out? Let's find out. We then look at the factorizations. Oh my goodness, because they're integers. Only finitely many of these. So this means there are just finitely possibilities of combinations of these labels. Hence only finitely many possible separator lines, things that are going on for a given delta. We've thought about this before for a fixed form with a particular, a fixed form has a particular discriminant delta, which means that walking along the separator line, delta's fixed along the separator lines, discriminant. But now we're thinking about lots of different quadratic forms that all have the same discriminant delta. I don't know. Sometimes I don't know what's going on in chat. I quite like it sometimes. The chat's just off on this whole thing. I'm doing something not particularly chill, like trying to understand maths. Oh dear. And chat's just off on their own in joke that I'm not included in. Right. Okay. Right. Finitely many equivalence classes because there's finitely many forms. They're equivalent. They have to have the same discriminant to be equivalent, so you're looking at this connection of finitely many things. It's quite a strong proof that the number of equivalence classes is finite, because you can have, of course, finitely many equivalence classes on infinitely many things. Let's determine all the quadratic forms discriminant 60. Okay. So if they have three numbers the same, so 1, 1, minus 6 somewhere, then it's the same quadratic form. It's equivalent quadratic form thereafter. There's this rule again. Sorry, that if you have a point where if you know all three numbers around there, then first off you can work out the discriminant by doing the sum of the squares minus twice the sum of the pairs. So sum of the pairs, I do 1 times 1, I do 1 times minus 6, I do 1 times minus 6 again for the other one. And that gives me hopefully 60. Oh my goodness, it doesn't look anything like 60. Oh, it could be though. 36, 37, 38. And what is that? Minus 11 plus 22. Oh my goodness, that is 60. Hooray. So you work out the discriminant first. You say, it's one of the ones, not that many, with discriminant 60. Let me look at my table with all the possibilities for what goes on when this discriminant is 60. H squared is bounded between 0 and that number divided by 3. So there's not that many things to check. Also, if you want to explore the rest of this, the values of this quadratic form, there's this rule that to walk across here, you go something like 1, and then reading the 2, there's the hard bit, reading across this line here. I should draw that differently. I should draw this it's so hard to draw. This value is 1. It's because the 1 is really far away. I want to draw this like going across. So it goes 1, and then the sum of these is minus 5. So then this minus 11 comes because A, both of these, and C are in arithmetic progression. 4. 1 minus 5, and then 6 less again is minus 11. And you can keep doing that to do this kind of 6 minus 10. And then on the other side, minus 14. I say minus 10, adding up these two. Across the middle one, the pattern is you do A, and then the sum of these two, and then C. So sort of add these things. A, to the sum of those to that one is an arithmetic progression. Reading across something like that in your binary tree. So you can work out all the rest of the values. And if there's only finitely many of these kind of things going on, values of P, Q, and H. H here is the difference, which I think I just said was minus 6 or something. 1 minus 5. So we're going to see, I hope, a way to tell us which of these equivalents, which of the cases from 3 values it is in the equivalence class. So I think because there's these 2 different possibilities. Look, this one that starts, this one that has, I would say, values around a 0.11 minus 6. That's an interesting feature. Has discriminant 60. So does this one. Sum of the squares. I don't want to add up the sum of the squares of these. 49, 49, and 4 is 102. But then subtract twice. 49 minus 14 minus 14. So 49 take away 28 is 21. Quick maths. We had 102 and we take off 2 lots of 21. That gets us down to 60. So this one also has discriminant 60. Whew. But they never take the same values. So this one repeats like this. After here, if you keep exploring to the left, you get these things. So along the separator line, it has values like 3 and 7. Whereas this one as you keep exploring, you never see 7 as value, or 3, and you certainly never see 7, 7 minus 2 around a point. So the big question, the thing I would like to understand is, can we tell from the values or some other analysis whether the quadratic form that says 1, 1 minus 6 at a point is equivalent to the one that says 7, 7 minus 2 at a point, or not? Essentially, I'd like to know how many equivalence classes there are, whether you can detect in some sense which one you're in. I'm not sure if there is a good way to say, to name the equivalence classes. We're going to find out, I think. At the moment, I have this quite hazy view about, like, if you see 1, 1 minus 6, or if you see 1 minus 11 minus 14, even that's not obvious that they're going to match up, and it turns out they're right next to each other in the topograph of the quadratic form. Right. So they're finding loads of equivalence classes on screen. To see whether there are others, we use this formula. Okay. Yep. So we're going to do our search, I think. Various possibilities. Okay, so these are values. Let's see if we can match these up to the pictures. What are they telling us? So they're telling us the value that h could be. H is kind of invisible. It's the difference in the values of the arithmetic progression that goes 1, minus 5, minus 11. So the difference here is 6, minus 6, or maybe 6 if you read right to left or something. So I suppose when at that point I have values of p and q 1 and minus 6. But this is, oh my goodness, the notation here is that the values of p and minus q. So I should be looking at maybe 1, 6, maybe 6, 1. Does it matter? These are positive. So I'm looking at, over here, I'm looking at the values of p and negative q, where p and q are both positive. So 1 and 6 in that order. So I can see over here, I suppose I should label bits of edge or something now. This thing is this. So we're in this case, well, we're at this point right now. If I then look further down the separator line, over here, the arithmetic progression now goes minus 6, minus 10, minus 14, which is a common difference of 4. I'm at a bit of edge over here. 1, the values are 1 and negative 11, and h is 4. So that's this. And then over here I can see 1 and 14, and I think the value is minus 2, or 2 maybe. Let's match my line styles. And then over here there's a 15, and I think the value is minus 13. Oh, right, okay. I thought it was going to be minus, no, so going across to the next one is over here, there's a minus 14. Drawing on the kind of periodic continuation of this thing. Then reading across minus 14, minus 14, minus 14 is like a 0. So curly line, highlight that one. That's this case. Those are all the first ones because I'm reading around this 1. I should have just looked at the 1. And then it goes back again. It goes back the other way. So it kind of wombles around these cases together. Each one of these occurs because you can start drawing. If you know H, P and Q, you can draw in P and Q, and H tells you about the arithmetic progression, how to continue. So they tell us how to continue. So if you find a value like this, and good news, you can go and build a quadratic form that does it. That's weird. Yeah, no, you can, because you'll work out the third value using H for your arithmetic progression stuff. Keep doing arithmetic progressions. When you see the 3 values, you can write down a quadratic form that does this. I kind of need to make sure that there exists a quadratic form that does this, that takes those 3 values. I know they all have the same discriminant because of some maths we did last week, but is there actually an example? Yes. Choose the coefficient of x squared to be one of the numbers, choose the coefficient of y squared to be the other one, and then think really hard about the coefficient of xy to get the third one correct. But I think you have those 3 degrees of freedom, so you can make the values at 0, 1, 1, 0, and 1, 1 be the 3 values you want. Whoa. You got 4 seconds lag. So there's quite a bit of lag, I think, between typing something in Twitch chat and it appearing up there and getting rebroadcast back to you because of... Does it have to go over the internet kind of 3 or 4 times? Quick think. If you send a chat message, you have to get it to Twitch, and then Twitch has to send it to me, and then my computer recompiles it into a dark blue box, sends it back to Twitch, and then Twitch serves it to you. So it has to do 4 internet journeys. Kind of amazing, really. Anyway. Not quite live. Yeah, 3-4 seconds. Am I artificially lagging it? I can't remember. There is an option somewhere to add extra lag in case I want to have the option to, like, I don't know, if something happens and I need to, like, delete 3 seconds of stream before it goes out. I don't have a button for that. Maybe I should. If I say something really stupid about fractions, it's gone. Right, services that I should look into. Things to hide my stupidity. Right, 7. What am I doing? 7. So this one. Okay, so over here, let's circle things. So I can see 7, 2. I can see 3, 2. There's 3, 2. 3, 2's over here. 3, 5 is part of this kind of collective. Is it going to loop round? Oh, I thought it would loop. Interesting. 7, 2, 7, 2 again, and then 3, 2, 3, 5, 3, 2, 7, 2, 7, 2. That's cool. And then we haven't discovered the other ones yet, but we could go and build them. I think I can make it sum to 60. So if you have ABC around a point, I want an example of a quadratic form that does that. I think I do ax squared plus, going to think, xy plus cy squared, because then it will take the value a at 1, 0. It will take the value c at 0, 1, and I'm not done yet. I'm going to check that at 1, 1, I'm hoping I can make it take the value b at 1, 1. At the moment it takes a plus b plus c, so I'll make this b minus a minus c, and then I'm good, I think. B minus a minus c, because then if you've been 1, 1, you get a plus b minus a minus c plus c for a total of b. No fractions required. Good for making it. Thank you for making me write it out, though. Good to check. And these 3 points are these 3 values are good. Oh, when you work out what you want b to be. No, back up a step. So if you have an edge where you know the value of h, that's supposed to be the difference in our arithmetic progression. Reading from here to, well, I don't really care about this bit, but reading from here to here is supposed to be a difference of h to that sum. And then the next thing over here is, I think, arithmetic progression, just add on h. So a plus c plus h. I don't know why I called them a and c, that was a weird choice. But I think this value on the right hand side would be a plus c plus h. If you start from just this edge, knowing the values above and below, like 7 and minus 2, I've picked this one that I haven't calculated yet. Let me quickly think. And the difference minus 2 for h. I guess maybe I'm reading right to left or left to right or something. The difference of 2. Then the next thing you get is 7 plus minus 2 plus 2. And you get 7. So this is 7, 2, but with a value of h of 2. Possibly I should be pointing at this edge and working left to right because I prefer to work left to right. That's how I write stuff. So I'm possibly pointing at this edge and saying, you would generate this picture starting from 7 minus 2 and then number 2. You just add. So that's also an edge. I've written it really small, a plus c plus h. Hope that's all right. Good to check. I think given a value of h, p and q, you can start drawing your diagram like this, or is it minus q? Here's minus q, and then get minus q minus over here, minus p minus q minus h, and just walk from there and keep going. Find something with these three values. It looks a little bit like that might cancel out some of my weirdness with all the minus signs, but possibly if I feed that through my other minus signs, then everything works out quite nicely. Plus or minus signs not entirely good. Px squared, qy squared. What do I want here then? Is it just plus hxy? Yeah, I think it might be. It does cancel out my weirdness. Okay, good. 1, 1 gives you the plus h. 1 minus 1 subtracts the h. Yep. Yes. Yes, so this table has h in it, importantly, down the left. Good. Okay, we're learning about quadratic forms, I think, which has been what I've been trying to do all year. Here we are. Oh, there it is. Look, on the board. Was that there all the whole time? Of course it was. It's just like a curse, right? I think I'm doing something original or my own invention of trying to understand it, and it's right there on the screen. Could you see that? That was there. This thing that I was just proud of working out. Oh well, never mind. Construct separator lines. Oh, it's on the screen. Look at the screen. I think just eyes as an emoji would probably work for like. Try looking at what's currently on the stream. Just eyes emoji. All right, good. Quick test run. Okay. If the stream froze, it was possibly me freezing in horror at doing something that was on screen. Anyway, happens a lot. So I haven't understood these cycles yet. Let's read. Eyes. Each pair of values in the table occurs at some edge. Yes. Every form of discriminant 60 is equivalent to one of these 4. We already found them all. In one of the two top graphs shown above for the negatives. So we've already found them all. But where did those two come from? What are we doing? We could have used the other ones to generate new ones. Okay, off we go. Like we were saying, good. List of all of these. Construct separator lines. Yeah, doesn't have to be a tick. You've got all the possibilities? No, yes, it has to be hyperbolic. What am I saying? Okay. Different separator lines give you different equivalence classes? Yeah, okay, I mean, fair enough. If they're equivalent, they'll have the same separator line. Right, organised into cycles corresponding to pairs p minus q occurring along one of the periodic separator lines. So I think this is trying to describe this behaviour where you go from PQ. Oh, so I want HPQ is kind of has this kind of cyclic behaviour. So this goes to, where does this go? So I think we saw. So if you walk along the separator line, actually the next thing you see is another one of these. Oh, but with h minus 2. Oh no, I'm puzzled. Possibly with a minus 2. Possibly with negatives. It's not like 10 seconds back. Possibly reload, and you might get back to the future. Okay, 4 cycles along the 4 different separator lines. We haven't shown pictures of the negatives of these ones, but I'm not that excited about the negatives. Or maybe I am for hyperbolic forms. Belongs to one of the cycles for the discriminant this, exactly when A is positive and C is negative. It belongs to one of the cycles for the discriminant this. Exactly when. So if it's not these, then your hyperbolic form. What do you mean it doesn't belong to the cycles? What? It's happened before, Maths 2 that people have said things that are faster than I'm thinking. The stream might be quite slow, but also so am I. So the race is on. Watch VOD. Oh, I should update the VODs. Good reminder. Sorry if you've been watching the VODs on YouTube and you're about a month behind because I forgot about them. Thanks for watching. As a message to the future. There you go. You see, you can send the message to the future, and then when it turns up, it'll be the present time. I don't understand this sentence at all. A hyperbolic form, and then just this says this. It says it belongs to one of the cycles for the discriminant this. I mean, if it is hyperbolic, that is its discriminant. So it has to belong to one of the cycles. Is this just a fact about hyperbolic forms? No, because there's only half of them, right? Where A is positive and C is negative. Hello, Super Snowman. You're right. Exactly where A is 0. I'm reading a puzzling sentence about hyperbolic forms. Since A and C are the numbers, I think it might be this symmetry breaking thing we've done to label only half of them, sort of P and minus Q. Well, let's see. Let's read the since. Since A and C are the numbers P and minus Q. If they're the other way around, then I don't understand that at all. Lying on opposite sides of an edge of the separation line when x, y is 1, 0, and 0, 1. Hyperbolic form belongs to one of the cycles for the discriminant, blah, exactly when A is positive and C is negative. No. I think I might be saying that too, literally. Because I think if you multiply by minus 1, actually, maybe then, so then it will belong to a different cycle. Maybe I'm misunderstanding what a cycle is. Pairs P minus Q. You have to do it with that. Ooh, Super Snowman's doing the egg problem again. The egg problem's been going a long time. I was thinking about the egg problem recently, but not in a way that I've solved anything. What was our best state? You had some research that you'd done, I think, to solve the Super Snowman. I think you had solved a couple of versions of hard problems like 8 choose 3 or maybe 10 choose 3? 2k choose 3. Right, okay. The egg problem is the following. You have a long egg box. It's not really what egg boxes look like, is it? A long egg box with some slots in for eggs, and you have some number of eggs. In this sort of case, this is 6. There are 6 choose 3 places to put the eggs. You can move one at a time, only one space, and your job is to, so the question is, can you traverse all 6 choose 3 arrangements? That's not phrased very well, sorry. I've phrased it better in the past, I think. What I mean is, I'd like you to take a photo and then move an egg, and take a photo, and then move an egg and take a photo, without repeating any of the photos as you go. So you can only move an egg one at a time, and you're trying to do a sort of Hamiltonian path through all of the possibilities. Sometimes this is impossible by sort of parity arguments, and sometimes it's possible, and it's a bit like solving a maze. That there's some connections here, because from this position I can move, well, there are 3 legal moves. I can move this egg forwards, or I can move that one back, or I can move it further. Except if I move it back, I've already been there, so no retracing that. Yes, is the graph of all the states Eulerian. The graph is all of the n choose r possibilities for n slots, and r of them have eggs in, and the connection is if exactly one egg moves one space. Yeah. Oh no, right, okay, oh dear. So in the 6 choose 3 case, or I suppose in the 2k choose 3 case, you can do this great 3D visualization. I'll do the 2 case. So the thing I remember doing is in the 6 choose 2 case, you have a kind of state space of where are the eggs, and one way to lay that out is a kind of grid. The first egg position might be something from 1 to 6. So 2, 3, 4, 5, 6. These are states, not to be confused with actual egg positions. And then the second egg position might be something from, well, depending on these different cases, I guess it can't go as far as 6. The left egg can only go as far as 5. And the second egg actually has to be in a higher number, doesn't it? So it's going to go 2, 3, 4, 5. So those are the possibilities, and then that next one's not really there. 2, 3, 4. Get this right. 6. So if you have this state of spaces, if you have 6 choose 2, so 2 eggs, 6 spaces. And if you want to try and traverse this, you're going to have to start maybe at one of these ends and walk through the maze, visiting every room to try and get to the end state. But you can't because of parity arguments. This is the bit I remember. The parity argument goes something like, you colour in, is it this way round? These ones. Now every step you take changes colour, but there are 5, 6, 7, 8, 9 coloured in nodes and only 6 uncoloured nodes. So you can't alternate properly to get from here to there. Alternating would give you one more of these than those, but you want to visit 9 and 6, so problem. Minor tangent. Oh, and Phobos Streamer's here. Hello, Phobos. Good to see you. We're upping the thing. Right, okay, yes, we've gone on a slight tangent. In fact, there are more than 2 of them with an odd number of connections. We're not trying to do Eulerian, we're trying to do Hamiltonian, which is quite a lot harder, I think. Eulerian, you would just count the connections. We're trying to draw all the edges, but we're just trying to visit all the states, so we can take photos of the egg box. This is an old Chalk Dust article that I did. Was it Chalk Dust? No, it was a periodical math eggs. I should just linked, shouldn't I? There you go. That time during lockdown when I did something with eggs. Right, I think I put a lot of. Oh, I actually recorded some GIFs. Goodness me, I don't remember doing this. Here's me moving an egg one space very carefully. This is a legal move. You can move it one square very carefully to try and get through all the possibilities. And spoilers, there's a graph in 3D. Got a kind of triangle at the top, smaller triangle, very small triangle, and then traverse it, and then, oh my goodness, there's some photos. That's what we'd like to do. And then the question for everyone, I suppose, was, when can you do this? You want the GIF? You're just very careful because the eggs, right? This was lockdown. It was not super easy to just feel, oh, I'm just going to get N more eggs. I don't know how to save a GIF. Right, we'll post it somewhere. Oh, I've no idea how dual graphs work. Good luck. I would love someone to just tell me it's really easy, just do the dual graph and then Eulerian. My feeling is that finding Hamiltonian paths is actually really hard, so we're going to be alright. I think it's a challenge. Yeah, okay, so reminder, Super Snowman has done, I think, 2n choose 3 in the notation where I talk about how many states there are, which is not a great way of describing them, but 2n comma 3, boring. Other cases are available. Right, what are we doing? Should we do some hyperbolic forms? Yeah, it's good to get distracted sometimes, because it reminds me there's other stuff, and I don't have to always think about this sentence, about whether or not it belongs to a cycle. I think I'm going to ignore this sentence. I'm just going to ignore it. Right, let's think about this then. Superimpose the separated line of the hyperbolic form on the associated infinite strip in the fairy diagram. Let's combine together everything we've done so far. Page 124. See, the forms within a cycle. Forms within a cycle. So I'm thinking about this. Forms within a cycle. So this is what I think about now. Moving from edge to edge. Yeah, so I suppose when you see an edge with values of p and minus q and h on the edge for the difference of the arithmetic progression, there exists a canonical form that does that. That px squared plus hxy minus qy squared. Kind of an example of a quadratic form that has that edge with that annotation. It's not the only one. The thing about being equivalent means that all the equivalent ones have that edge somewhere. So, I think the way they're talking here, though, is to say, along the periodic separation line, you have different edges, which corresponds to different quadratic forms, which is not quite how I think of it. Though you have one quadratic form, and then you look at the edges. So possibly I'm misreading this, or misinterpreting this, or possibly it is trying to think about it in a different way to how I would like to think about it, which is sort of one quadratic form, lots of edges, the cycle, and some of the edges that you might see when you make an abstract list of edges for that discriminant. But it's not going through different forms as it goes. There's one quadratic form that we're looking at. They would like to think, I suppose, about the canonical form for each edge. Maybe the forms within a cycle. I think one particular form cycles through different edges. They might correspond to the edges of the fairy diagram that line the strip and join one border of the strip to the other. Last week someone came into chat and said, but you have a PhD, shouldn't everything be really easy? So, bad news. Doing a PhD does not make things easier. Right, what is this? Fans of two triangles. Alternating with fans of three triangles. I've got to remember, in dotted lines here is the topograph. Joining triangles together with a point inside each triangle. I've got numbers that lie in regions of the topograph because they correspond to fractions from the outside of the fairy diagram. And I had those numbers on the corners. How did the big fan thing work? In the fairy diagram, we had those lines that were... What were all of these? It's been a while, but we had fractions labelling these points, didn't we? Not whole numbers for evaluating a quadratic form, but we were thinking about the fairy diagram with fractions for what these points were. We had the median rule for increasing things along the fans. We see the forms within a cycle. So the forms within a cycle, I would say, is this bit of the separator line across here. Oh, and each time we're crossing one of these lines, okay, maybe that's what I'm looking at. Join one. We see the forms within cycles correspond to the edges of the fairy diagram that lie in the strip and join one border of the strip to the other. That is these diagonal lines. I'm trying to understand this phrase. I'm going to read that as diagonal lines. Not the horizontal ones, the diagonal lines. Right, okay, so the forms that within a cycle, which I think means forms within a cycle, I think forms within a cycle means edges of separator line. I'm thinking loosely about those corresponding to different canonical forms. Correspond to the edges of the Faro diagram. So each one of these, it's joining up to areas. And there's a line that goes across diagonally, because these lines join. Yeah, so I haven't understood the thing about positive and negative. Separator line, the separator line has some correspondence to, well, I suppose. So I'm still thinking about continued fraction for the place we're going to, and I shouldn't be thinking about that right now. I'm not quite. Can I change the settings so that the likely ban evader restricted just gets banned straight away? Can I also moderate their comment? Oh no, is it invisible for everyone else? Just me. Right, great, okay. I should probably get a mod or something, shouldn't I? Right, I think there was an invisible chat comment. Did you see it above? I can't tell. Right. What on earth am I doing? The situation can be improved. Right, okay, here we go then. We've got these diagonal lines, and for some reason, no, for the good reason that this is just, you've got triangles everywhere. You've got this beautiful triangular thing. Topologically, you have a triangle with triangles, with triangles, with triangles. Oh, I could just draw the spider and loads of triangles. Topologically, you just have triangles everywhere. Are they like that? No, it's not 6 at a point. They keep going. Every edge has new ones. Oh, crinkly geometry. Not tiling the plane. The triangle has new triangles, and then you have to try and fit new triangles in here. So people draw them flatter, I suppose. And then new triangles around all of here. So more like a snowflake than the tiling of the plane. There was a misbehaving bot, but it took me ages to work out that no one else could see it. So it was all ghost bot, just around. Right. Maybe I should mod marry. Forms that correspond to separate pairs of adjacent fans. Right, here we go. Let's clear the start. We're going to think about this. So, number of forms within a cycle can be fairly large in general, because it can take a long time along the periodic separator line before we get back to the same thing. I think I've seen that happen. Only considering the most important forms in the cycle, the forms that correspond to the edges in the strip that separate pairs of adjacent fans. So these thick lines, right? Heavier lines in the figure above. In terms of the topography itself, these are the edges in a separator line whose two endpoints. Edges in the separator line whose two endpoints, and I'll tell you where you go. Two endpoints have edges leading away from the separator line, horizontal, in different directions, on opposite sides. Yeah, the forms corresponding to these edges are traditionally called the reduced forms. Right? Okay, we're learning a word. Reduced forms. So where the point these right? Okay, two endpoints leading away from the separated line on opposite sides, which for us is going to mean that the values somewhere. My goodness. The values have, there's some inequality here. It's going to be on screen somewhere. Don't give me the eyes emoji yet, but there's going to be some inequality here to say you've got some value and h is such that the next value over here is the same sign as that one. Oh, maybe. Could be tea time. Right. there's going to be some condition on h, I think, to make sure that over here this thing has the same sign as this. What do I want then? So I have p h q, p plus q minus h, p plus q plus h. We want, also p is positive, we want p plus q minus h positive, and we want p plus q plus h to be negative. Doesn't look very, so h less than p plus q, but not as much as negative p plus q. So it's going to look, I think, a bit like mod h less than p plus q. So it's minus q. I always get that wrong. Let's put minus q everywhere. Do I need to put multipliers from my p minus q? Oh, now I've got to think. Now I've got to think, he says in a worried tone. This is annoying that there's all these. I would definitely want these. P minus q minus h. Positive. No. Plus h. Oh, the one with plus h over there to be negative. And I want the one with minus h to be positive. Fun! So I want h to be less than p minus q. But I also want h to be less than q minus p. Good, right, okay. If you want to play along with the egg thing, you also need to construct, you'll realise quite quickly that the egg box I'm describing is not a normal egg box. I had to chop an egg box in half because I designed a problem that was different. People have in the past thought about egg boxes that are egg box shaped, where the connection graph is a bit different because you can do vertical moves. Different problem. Have I sold some eggs today? Right. Speaking of sponsorship or monetization or whatever, great. But we're going to come back to the values that p, q, and h can take in order to give us a reduced form. I think I'm getting somewhere. I could look at these, I suppose. But these are also canonical forms, right? Because there are things equivalent to these. Forms corresponding to these edges, but that edge occurs in lots of quadratic forms that are equivalent to this one. Technicality, but I think this is a representative of the equivalence class in a particular shape with A positive and C negative, which has thrown me a bit. So like this one, these look the same, right? Are they not the same? Under some sort of symmetry flipping stuff with a minus sign out the front, which means all the values are negative. Yeah, I think flip the signs of y and the quadratic. And that gives you a change of the sign here. Oh no, because then you get minus. No, yeah. So you change the signs of y and the quadratic itself, and that's two reasons to change this sign, which is why it's still 6. One reason to change this one. Also swap y and x. There you go. Now I'm there. Swap y and x. Change the signs of one of them, and which is a reflection, and put a minus sign in front of all your values. And two of those are just equivalent transformations that will give us an equivalent quadratic form, but the last thing of put a minus sign out the front gives us inequivalent. Almost the same, but just negative values. Right, okay, and this. In this example, oh no, there's just one reduced form for each cycle. But in more complicated examples, there can be any number of reduced forms in a cycle. Do not necessarily give the simplest looking forms. Right, time for a tea break, I think. What's the point of these reduced forms? You can have multiple reduced forms in a cycle where the fan does like weird stuff backwards and forwards. You get multiple reduced forms in a cycle. I suppose if we can look at your quadratic form, reduce it in some sense, then that's like finding a special bit of the graph, special bit of the topograph. Or alternatively, these. Right, brilliant. Okay, tea break. Speaking of all the monetization, That was weird, wasn't it? I did the segue and then I forgot I did the segue. So I said, speaking of monetization, did a bunch more stuff about quadratic forms. Speaking of monetization, I'm going to run an ad break and make a cup of tea. Because Mary says I should make a cup of tea. Thanks for 20 points on tea. Right. I'll be back in a couple of minutes. In between, there's a chance that you see an ad. If that happens, then long term, the ads are supporting charity. Because if this Twitch stream ever cashes out, then A, that would be hilarious. It's a math stream. Can't get cash off a math stream. And B, it's going to charity. Right, okay. Can't get money off a math stream, and I will make sure I don't. Right, okay, here comes some ads. See you in a couple of minutes with a mug of tea. You might like to make a cup of tea as well. Good, right. I'm pausing the stream. I'm back. Did anyone get any good adverts? Oh, they got adverts for. Mary got 5 adverts getting ad breaks. And then something about Parrot. Right, here we are again. I think I've unmuted and come back. Goodness, before the stream we were looking at reduced forms, which I hoped would be a kind of representative of each equivalence class, because I thought we were going somewhere. Maybe we would look at our quadratic form and identify which reduced form it corresponded to, but there are several. So we have now a list of several edges you might have, important edges, but you could have several of those. So it's going to be quite tricky, I think. Okay, let's think a tiny bit more about these inequalities. Have I got them the right way round? Yeah, good enough, I think. Good enough. Minus q is negative. Yeah, good, okay. Right. And no ads, just the back soon screen. Okay. Oh, right, okay. For zero hyperbolic forms, it's rather easy to determine all the equivalence classes of forms of a fixed discriminant. I can't remember what's going on with zero hyperbolic forms. Which ones are they? They take the value of 0 somewhere, and also things of both signs. Two regions labelled 0, and the labels on the regions adjacent to each 0 region form an arithmetic progression increment given by the label on the edges bordering the 0 region. We're now going to call it Q instead of H. We were already using Q for so many things. The discriminant is Q squared. So both 0 regions must have the same edge label Q. Oh, goodness me. Either one of the discriminant's the same, Q's positive without loss of generality. Good, okay, so when you see the discriminant's the same on both 0 regions. Two successive terms in the progression together with the 0 in the adjacent region give 3 values and you're good. Here's a form that has discriminant Q squared, 0 minus Q squared minus 0 is Q squared, has minus P as one term of the arithmetic progression adjacent to the 0 region. So what are they telling me? You have a 0 region, there are 2 numbers to worry about. They are at some point think about the value opposite, the value adjacent to the 0 and the edge, and you can work out everything from there. And here's an example of something that I think they're going to tell me does that. Yes, I think that is what they're telling me. Here's an example, a kind of canonical form of the quadratic form equivalence class that have 0 as in a region and have edge label here Q and value, what's this? Two successive terms in the progression together with 0 in the adjacent region give the 3 values of the form around the vertex and the top graph. These long sentences, aren't they? The form has discriminant Q squared and has minus P as one term of the arithmetic progression adjacent to the 0 region, like this, minus P. So once you know this stuff, you've got a 0 region, you've got minus P adjacent to that, and you've got Q as the kind of difference in the arithmetic progression. So then you're going to keep going and generating all the numbers from there. That's enough. And these two, I think, could be anything. So we're going to characterize these by saying, for a given number Q squared, there's an equivalence class. Oh, not quite an equivalence class for each value P, right? Because they could lie in the same arithmetic progression. Okay, let's read on. Every zero hyperbolic form of discriminant Q squared is equivalent to one of these forms. Just one? Yes. At least one. Haha, I think I've got them. Because then, look, this is telling me about increment Q can be thought of congruence class as mod Q, so only the mod Q value of P affects the arithmetic progression. Right, here's a restriction. So when you say one of these forms, you mean at least one because I can increment P. Cool. Right. Phew. Emojis. Oh. What is the 6-3 order? Do you mean the solution to the egg problem? I'm going to link it again. The solution to the problem is in this link again. Or a solution. There are several. Well, you have to go through 20 states. For 6-3. As well as recording a silly GIF, I also took photos of the 20 things and then sorted them into the right order. A correct order, sorry. it's traditional. If you've been pedantic about something, it's traditional to then make the same error yourself almost immediately afterwards. So they say one of these forms, I say, oh no, it's actually at least one of these forms. Then later I say the solution when I mean a solution. Good. It's symmetric, right? Okay, at most Q, because there's not that many arithmetic progressions. Number of congruence classes mod Q. Ooh, could be smaller, since each form has 2 zero regions, and hence 2 arithmetic progressions. Can you have arbitrary choices of both, which is that's quite fun. Could be the same or different. This is like a quadratic. I'm imagining a quadratic with 2 rational roots. Because then there are places where it takes positive values, places where it takes negative values, and 2 places where it takes 0 values corresponding to its 2 rational roots. We found the rational roots way of understanding quadratic forms, which I think is my preferred way at the moment of thinking about the different cases. The parabolic one is repeated roots, for example, that's rational. Yes. Okay. Yes. 2 of these could be the same. They could be the same. So the question I think is, can you get an arbitrary pair of different arithmetic progressions? Either arithmetic progression determines the form. Ooh. So that says no, right? You can't have an arbitrary choice. Because if you set up the 0 region with one of them, then you will discover the rest of the topograph. We've said several times now that if you start with a point and you know the 3 values around it, 0, 2 values of the arithmetic progression, say my discriminant is 25 and I'm thinking about what's the difference 5, so it might go 1, 6, 11. From there you can generate everything. So it can't be the case that you have another freedom of choice about which arithmetic progression. I want that one to be 3, 8, 13. You either get that one or you don't. Maybe they have the same. Maybe they pair up. Maybe it's just the same. That'd be tidy. Or maybe they do some weird pairing. 2 progressions are the same. Then the topograph must have mirror symmetry, interchanging the 2 0 regions. Oh, yuck. Yeah, believable. Okay. This always happens if the 2 0 regions touch, which is the case P equals 0. So the form is equivalence to this one. And mirror symmetry just interchanges X and Y. If we let R denote the number of forms without mirror symmetry, then the number of equivalence classes of 0 hyperbolic forms are discriminant Q squared. Well, I don't know how many that is though. It's Q minus R. Since each form without mirror symmetry has 2 different arithmetic progressions giving the same form. So there could be some pairing, okay. Mirror symmetry. Yeah, okay. Right, it's all of them minus the ones that aren't there or something. It's sort of a little bit circular, right? Oh, I don't know how many there are without mirror symmetry. I'm not sure I consider that done, but hey, here we are. For parabolic forms, these are ones with a repeated rational root to the associated quadratic for x over y. Long phrase. Getting so good at the English language, aren't we? Chill English stream? We could do that, it'd be fun. Just chatting. That could be what we call it. Just chatting. If only there were a category on Twitch for such a thing. I think I've invented something great. A stream that's just practicing the English language by talking loads and loads. No one's doing that. You're not going to come to me for getting accurate phrasing, are you? Right. Did I remove the English tag? I was looking at my tags just now. I have a tag of English. I'm tagged mathematics, maths, English. I'm in the just chatting category. I can't even say in the. There we go. Twitch settings. Would I like any crunchy rolls? Good. There's a single region labelled 0. Look, I'm struggling here. All the regions adjacent to this have the same label Q, so just choose what that is. It could be anything. You're good. Here's an example of one that does it. You're fine from there. All have discriminant 0. The picture for this is a region 0 that just says Q, Q, Q around it. And then if you're parabolic, you've got a 0 region with constant values around. Find out what it is. We saw this before. We could multiply up by 3 or something and get the same. Well, not the same, but to get a different one. Maths is a universal language, right? Oh, I don't. Yeah, I have strong feelings about that claim, having just made it. Infinitely many with the same discriminant. All have discriminant 0, whatever. Okay. Only look at primitive forms. Ooh, can I remember what a primitive form is? No. Possibly ones that take the value of 1. Maybe. So this is quite powerful now. It says if you have a parabolic form and you want to know what values you can take, you work out its equivalent to one of these. So the answer is squares multiplied by some number q all the time. No, that's true. We sort of knew that before a little bit, but fair enough. People sometimes say emoji are universal language, but it's pretty hard to say anything with just emoji, really. The classic retort, which I think I got from Gretchen McCulloch, is if you think emoji are a universal language, then tell me that emoji are a universal language using emoji. Right. Who is this Ice Cube? Emojis are really hard to read. Yeah. GT context clues. Oh, right, okay. Off we go. Chat's going to talk about emoji for a bit. I'm going to talk about quadratic forms. Feels safer. Right, okay. Every parabolic form is equivalent to one of these by changing variables. Oh, okay, yeah, fair enough. This is the... Is this the source of linear fractional transformation that we've been doing? I think it might be. So every parabolic form factors like this for some pair of coprime integers s and t. Q is plus minus 1 for primitive forms, fine. Similarly, every zero parabolic form is equivalent to a form this. What? Oh, okay, we just do a transformation or something. So the form that you have these transformations, go for it. It was a simple enough thing, wasn't it? And then you do a linear transform. So the form can be written as like this. Oh, no, this is us doing the transformation, which looks like a product. Here are the roots. Amazing. Parabolic forms, okay, so the two linear factors are the same. I'll do a constant multiple. Repeated roots, hooray! My preferred way to think about these. Good, okay. Okay, the following fact. Only a finite number of equivalence classes of forms with a given non-zero discriminant, because of the fun with the parabolic ones. And that's the end of that section. We get some exercises to repeat this with different numbers. I'm not going to do that. This is chill math, so I don't do the exercises. Discriminant 49 is a positive square, which makes me think that we're in the case where... Which one's that? Is that zero hyperbolic? No. Yes. Yes, that's zero hyperbolic. So it's the ones where... Oh, right, but we've actually got to think whether these pair up or not. So we could try using that Desmos tool that we got from Maths22222 in chat. Let's see if I can find it. It's this one, right? Sort of like this. Okay, right, so I've got this tool that lets me just evaluate them everywhere. And we're being asked about 7xy minus py squared. Right, I hope I can use the letter p. Yeah. So p is 0 to 6, step size of 1. So we have these different forms. Can I zoom a bit? There we go. So I think they should be 0 twice. Is that true? I guess when, maybe not when p is 0. Okay, so when p is 0, I get this one, which has values around here with common difference 7. When I set p to 1, these terms still have common difference 7. Oh yes, but starting at -1, -2, -3. Okay, so we're changing the sequence that you get around here. By changing this number, you always get a common difference of 7 going around for the arithmetic regression going around this 0 region, but we're changing the starting point over here. And then the question is that some of these are equivalent to each other, possibly, because sometimes you can find another 0. Like over here, there's another 0, look. So this is the one with -3 in it, but it's also got -5 next to a 0 over there, and then 2 and -24 and stuff. So -5 and 2 next to a 0, which is the same as if I set this slider to 5, like -5 and 2. And then, okay, and then a 24. So those two are actually equivalent. If I have 5 or, what was it? 5 or 3 give me equivalent forms. Hello, Blue Malt and Hops beverage, or if there was a D on the end, I would say Blue Beard, but I'm going to go, just Blue Beer then. The 0 is moving around slowly. Yeah, so we're changing. Yeah, okay. So as we change this slider, find the 0, I suppose. We kind of know where it should be in terms of a fraction, right? So the zeros of this, it says pause for effect where y is 0 or where x is p over 7. So there's these sevenths in here somewhere. 1/7 is in, oh, good thing we used 7, isn't it? Where's 1/7 in this picture? Possibly not shown. Is 1/7 over here, down here somewhere. 2/7. So if I set it to 2, then the 2/7 brings in this 0. Do I need more depth? This was made by Maths222222 in chat. Do I change this one to get more depth on it? I think I do. Yes. Label depth. Brilliant. Love it. Too much. Yeah, I think I need to go one step further to get the 7ths in there. Yeah, so there's 1/7. Maybe I need this number to go. Ooh, too much. That is a link to your computer. So I will go the what command. Or does it work if I shout? I think that's a link to the internet version. Right, okay, I've done all the fractions so I can see 1/7. So that if I set this to 1, there's the 0. And then the observation is that this 0 is also, the 0, changing some of these settings changes some of the totally separated line stuff. Let's forget about that for a moment. The 0 is also adjusted to a 6 in this case. Really not obvious. Really not obvious. And then if I change this to 2, it goes, there's a 0 over here. 2/7 is not as deep in the Ferri diagram. We have this like binary tree containing all of the fractions. 2/7 is around here. There's some logic for which fractions go where. Don't worry about it right now. 2/7. Yeah, 0. Oh, I can reset the colouring. Stuff to leave alone. I think I'm happy at the moment. Where's 3/7? I guess it's around here somewhere. 3/7. So I've set this to 3. There's a 0 over here, which is also adjacent to 2 and -5. So the 3 and 5 cases are equivalent. Oh, a bit of a mess, sorry. The 3 and 5 cases are equivalent. Oh, it labels all the areas as well. It's so good. It's so good. The 3 and -5 cases are equivalent. And there's this 4 case, are they going to pair up? There are 7 of them, so no, they are not going to pair up. The 0 case, the 0 case pairs with itself. The 1 case has a -1 next to a 0, but also over here somewhere, more depth, has a 0 next to, oh, I don't know what's going on there. Let's go one more just to explore. So what's going on over here? I love the way they become sort of diamond shaped. So what's this arithmetic progression going around this 0 with 6 and 13 and -1 on here? Oh, is this huge -1 region? So that one matches up with itself as well. That one matches up with itself as well. I guess the 6 one probably matches up with itself by some sort of freaky symmetry sort of thing maybe, that I haven't really thought about. Let's go and find 6/7 up here somewhere. Label depth. Show me 6/7. Yes. matches up with -6. Yeah, matches up with itself through possibly freaky symmetry that I'm going to think about. We think that 2 matches up with 2 matches up with 4. I can see a -4 over here, as well as this 0 and -2. 3 matches up with 5. So we have 2 pairs and 3 that match with themselves. That's weird. I don't know how we would have worked that out without either doing lots of sums to work out what's near the zeros, or doing some exploring, or just this tool lets us evaluate them loads of places. Oh, I have an old version. Yes, sorry. Thank you. That's my favourite part. The topology of the stream is almost as interesting to me as the topology of numbers. Did you change the labelling as well? Okay, so a different labelling. Good, right. Brilliant. I've ruined everything with a reset button. Good. I have to type it in there as well. Okay, good. Right. Okay. So this is the interesting thing that these things could belong to the same equivalence class as each other. I'd have liked it if that was just a list of the equivalence classes. But we're getting towards an idea of, what did we see? 2 and 5 joined together? Is it P and 2 and 5 joined together? Should we have another go? Just want to do it again, sorry. So 2 has this region with 0 next to a -2, and over here it has 0 next to -4. No, so it's 2 and 4 match up. That you could take this one, do a transformation of it, move it around, and so that the 0 was over on the left and the -4 was next to it, and then you would get this one with 0 and -4. And like everything else follows on from there. They've both got discriminant 49. So for example, they've both got 3 and -11 as kind of adjacent things. So if I put it back to 2 and zoom in, you have these regions 3 and -11, but it's sort of distorted and turned around over here. It's a transformation of the other one. Right, diagram V4. Excellent. What are my notifications? Oh, Crunchy Rolls. Brilliant. Okay, there's some questions, but we're too chill for questions normally. I think I get to read about class number, which I think might be a thing. Yeah, right, okay. One egg is possible for 9. 9 eggs is fine. 0 eggs we could put on that list, it's fine. 8 is sort of the same as 1. You're sort of moving air pockets around. I think 9 choose 2 is impossible. I think in general n choose 2 is impossible, except for n is something like 2 or 3. That's a big claim. That is a big claim. That's going to need a reason to back it up. 2 to the n plus 1 boxes. Claim being, there's so many states. No. 2 to the n plus 1 choose k. No, I can't tell you anything about 2 to the n plus 1. Gap, choose k. Oh, hello. Academy of Useless Ideas. Great username. Welcome to chat. I don't know, Conway's map of rational numbers. We've been calling it the Fairy diagram, F-A-R-E-Y, named after someone with the surname Fairy. It's related to the Calkin-Wilf tree. Possibly these are all the same idea. The idea is you start with, at the cardinal points, 1 over 0, 0 over 1, 1 over 1, minus 1 over 1. And then you fill in halfway between, you put the fraction where you've added the numerators and the denominators. And you keep going. So halfway between 1 over 1 and 1 over 2, you put 2 over 3. Which is not what you get when you actually add the fractions, it's what you get when you add the numerators and the denominators. The visualization that we're doing here is, it's been through several stages. We're reading a book called Topology of Numbers, which is pretty cool and includes lots of diagrams visualizing fractions as points on this kind of complicated diagram. So I'm going to go and just have a quick look again at the main diagram for what we're up to show Academy of Useless Ideas. He's just got here, and anybody else who's joined. You'd have to watch all of them. There's a lot. We've been reading this textbook for ages. Let me show you the one picture. Not that one. Oh my goodness, not that one. I think we skipped that. It's this one. The lines here are showing where you're adding in the midpoint. So from 1, 1 and 0, 1, add the numerators and denominators, 1 over 2. And you get this kind of binary tree. The other picture that we've been drawing is to think about all of these triangular regions with 3 usually curved sides. To think about the binary tree that you get that walks towards different fractions. That are kind of only 2 moves you need to get towards any fraction you like. There you go. That's what we're up to. There are then nice consequences in terms of, well, we've done some sort of transforms of this to move it to the upper half plane, to make lots of semicircles. We worked out some facts about continued fractions using this. It's a good textbook. We're currently trying to work out facts about quadratic forms, which is where you take the numerator and the denominator and you plug them into something of the form ax squared plus bxy plus cy squared, quadratic forms. The question we'd like to answer is, what values might that quadratic form take as you plug in all pairs of numbers x and y? And there are several possibilities, not that far back here. Ooh, underlined and overlined numbers, that's going to be fun. I think I want to go to 2, 3, 4. We are somewhere around here after the exercises. Down a bit. We are going to try and understand the fact that there are some nice transforms. So if you start evaluating your quadratic form, you might find that you're getting the same pattern of stuff, but the picture's been rotated or reflected, or this other strange transform that moves a triangular region somewhere else, using a transformation of the form az plus b over cz plus d, where those are all complex numbers, and ad minus pc is 1. Mobius transformations of the unit circle. Anyway, these are all, in some sense, useless ideas, but also quite connected, which is nice. I'm about to read the phrase properly equivalent. You know, we've been dealing with equivalent forms, but it's time to deal with properly equivalent forms. Okay, further refinements that turn out to be very useful. Mirror images, right, okay. We'd consider those to be equivalent at the moment. Mirror image, same values at a point. So same values thereafter. We have given 2 such forms of required as equivalent. Oh, great. Okay, it was on the screen. Eyes. However, there is a more refined notion of equivalence in which 2 forms are considered equivalent only if there is an orientation preserving transformation. No reflections allowed. Properly equivalent, no reflections. This stream we never reflect on anything, so that's good. It'll fit our vibe. To illustrate the distinction between equivalence and proper equivalence, let's look at delta is minus 260. We've got several of these symmetries now. We've thought about putting a minus sign on all the values. We didn't consider that equivalent before, and now we're going to split the hairs of orientation preserving. Whoa. It's a good book, and it is free. It's a free PDF online, and also free web pages. Hatcher is cool. Right. Oh no, well, I turned the page and it was completely different to what I was expecting. Right, okay. Earlier examples of discriminant. Oh yes, okay. 6 equivalence classes of forms. Here they are. 1, 2, 3, 4, 5, 6 of them. And here's a little picture of some of the values that you get from these quadratic forms. Nice. And right, so are we going to say that some of these have mirror symmetry somehow? Maybe this one has the repeated values? No, what are we going to say? Yeah, so some of these would split as an equivalence class, I think. So this one has mirror symmetry, mirror images. Right, here we go. Eyes, it's on the screen. For the lower vertex is a source vertex. Whenever there is a source edge, hey, thanks for the follow. Whenever there's a source edge, the topograph has mirror symmetry across a line perpendicular to the source edge. Okay. Now, we haven't got any labelling for source edges, but apparently an edge is sometimes a source edge. And you get these values above and below. Good, mirror symmetry. When there is a source vertex, there is mirror symmetry only when at least 2 of the values are equal, 33, 33, like I said, as in the 3rd and 6th, 9, 9, but not in these ones. No matching values. So the mirror images of the 4th and 5th correspond to 2 more quadratic forms, which are not equivalent to them under any orientation preserving transformation. It's going to be switching x and y, isn't it? Or something like that. More refined notion of proper equivalence. 8 proper equivalence classes. Okay. Fine. Interchange the coefficients A and C. That's swapping x and y. And now I'm thinking about, okay, so switching A and C. I was worried about this about an hour ago for a different reason, and now we're actually talking about swapping them to get a different form. Fine, whatever. Alternatively, we change them to B. Okay. Just like reflecting, yeah, across the horizontal line. Okay. Each equivalence class of forms of discriminant delta gives rise to 2 proper equivalence classes, except when the class contains forms with mirror symmetry. So there's this idea about mirror symmetry again. We saw it about half an hour ago. So you've got to count the ones with mirror symmetry, which creates equivalence and proper equivalence about the same thing, because you would do, yeah, how would I say this? From what I've seen so far, I would say something like when you reverse the orientation. When you reverse the orientation, the question is whether you get a new form or not. And I suppose I'm relying on the idea that although there are lots of ways you might reverse the orientation, those are all equivalent to each other because of transform of a transform is a transform or something. Groups. Orientation reversing is a quotient. Anyway, never mind. So if one of those is then revealed to be the same as the place I started, then all of them are equivalent. The orientation reversing ones are not the same thing. What are they saying in this book? Proper equivalence about the same thing, since every orientation reversing equivalence can be converted into an orientation preserving equivalence by composing with a mirror reflection. Oh, that's much nicer. I like that a lot. So after you're doing your suppose it needed an orientation reversing transformation, well, you can achieve the same thing by doing an orientation preserving. That's relying on the idea that you can then do a further transformation rather than backing it up. Okay. These are in fact the only linear fractional transformations that take a topograph to itself and reverse orientation and mirror reflections. I'm not sure if I was conflating those two or not. We're going to do symmetries in more detail later in the section, section 5. Multiplying a form up doesn't change its essential features in any significant way. This is what we think with the qx squared ones. And they're still not going to let me multiply by -1, but still. Restricted attention just to primitive forms. Okay. Forms that are not proper multiples of other forms. Oh, did primitive form mean not necessarily that it could take the value 1, but that there's no common factor in its coefficients in all 3. Yeah, there it goes. Okay. Just from the numbers appearing in its topograph. Since all the numbers in the topograph of a non-primitive form are divisible by some d, then the discriminant is divisible by d squared, right? Is that what we're going to say? Maybe not. If all the numbers are divisible by some number d, and conversely, if all numbers in the topograph of a form are divisible by d, then in particular, the values there are multiples of d. Okay, fine. That's not great. Detectable just by looking at everything and seeing if it has a common factor. Keep looking at everything. Could be a lot of stuff. I suppose look at 3 things at a point. If they have a common factor, then everything will, by arithmetic progression rules, to propagate out. So just look at three things. If they have a common factor, then your quadratic form's not primitive, and vice versa. Primitivity, how am I going to say this? Primitivity, I suppose. Primitivity. Oh, I can do that. Primitivity is a property of equivalence classes of forms. Practicing talking. Oh my goodness. Yeah, multiplies the discriminant by d squared. So you'll be fine. You'll spot it. I don't know if that goes backwards though. If your discriminant has a square factor, if it's not square free, I'm not sure it's the case that you can only generate non-primitive quadratic forms. In fact, I think we've seen discriminant 60 or possibly negative 60 generate interesting things, which are not all multiples of 4. Yeah, we've seen things like that. I calculated some of these, didn't I? Earlier today, we had something where the answer was 60. I had to do 102 minus 2 lots of 21. I remember that. It wasn't the case that everything was multiple of 4. Right, here we go then. The number of proper equivalence classes. We're in flipping is not the same. It's called the class number for that discriminant. Where in the case of elliptic forms, it considers only the forms of positive values. Isn't that loads? What? H has nothing to do with the other H. Great. Number of proper equivalence classes. Proper equivalence classes. Oh, for a given discriminant it's finite, because equivalence classes are finite and proper equivalence classes can only double things at worst. Right, so for a given discriminant you're okay. Okay. We have an algorithm for working them out. Yes, when we're doing that, for elliptic forms or HPQ for hyperbolic forms, omit the non-primitive triples. Since they'll give you non-primitive forms. Proper equivalence classes. Proper equivalence classes of primitive forms. Okay, 2 restrictions, or 2 changes. Proper means you get more equivalence classes because it splits some of them based on reflection symmetries, or lack thereof. And primitive forms means that I'm not interested in examples where... So there are examples where the discriminant was 60 and everything's multiple of 4. I'm not interested in those. That's the class number. Hooray! Definitions. Definitions are important in maths. Wow, learning new stuff is really hard. Here we are. Since we have an algorithm for computing the finite, so yeah, good. Okay, off we go then. Determine which of the remaining forms have mirror symmetry. That sounds impossible. So just looking at those values in the diagram stuff, I cannot tell you if things have mirror symmetry, right? Oh no, here we go. We're just being told it. Now, here we go. For elliptic forms, as we will see, we're always doing this. We're not going to see it now, we're going to see it in the next section. For hyperbolic forms, mirror symmetries can be detected in the separator line. Forwards and backwards. Yeah. And I've got a feeling that's going to turn out to be... Wait, so we've been saying this is... So it feels like it's related to the fact about continued fractions having symmetry forwards and backwards. Which we think is going to turn out to happen for ones where the root at the end of the rainbow is a quadratic irrational number. Which feels like it might be for these quadratic forms. So I sort of think the periodic line is always mirror symmetric. I think. Forms with mirror symmetry count once when computing a class number, if you're counting not proper equivalence classes, and forms without mirror symmetry count twice. Yeah, having an algorithm is not enough. Indeed, this is... Oh, right, okay, good. Good. I like it when this happens. A very difficult question, which is still only partially understood. Brill. I like it when that happens when you're taught. No one understands this. Huh. Is this the class number that I've heard about for other? Right. So maths 222 is telling me about eggs in chat. We're going to pause here at this only partially understood thing and switch to my eggs thing, which is only partially understood. They say that NCR minus Rn minus R. What's the R? What's Rn minus R? Parity for the sums of positions passing through them all. No. Sorry. R times n minus R. R times n minus R doesn't mean anything to me, I'm afraid. Oh, hang on. So you're trying to extend the idea of parity for the steps in higher dimensions, and you're telling me that Rn minus R. Is that no? No, I don't understand why you've done NCR minus R times n minus R. Here we go. Straight line via the sums of the positions of the eggs. Oh right, okay. So there's how many steps you're going to do to get there. Yeah, this feels like okay. So there's how many steps it would take if you just shuffled them all straight there. And we're hoping that parity is a thing. It's not obvious that it's a thing. Can you do a 3-egg shuffle to get? Can you do a kind of 3-egg shuffle to move around? I think you can't. I think it's just a higher dimensional tetrahedron structure for the graph. I think. Although something like what do I want? The parity is something like the number of eggs that have moved and the number of eggs that have moved an odd number of spaces forwards is the parity of a position. If you look at the position and the number of eggs that have moved an odd number of places forwards, is that even or odd? That's the parity of a position or something. So then you're checking the parity at the start and the end, and that should have the same parity as if we go the long way via all the places. Yeah, it seems reasonable. Yeah, I think this rules out a lot of cases. I can't remember if we already knew this or not. There's a document somewhere. Ask Super Snowman in chat. I wonder if they're still here. Super Snowman, I think at some point ruled out about a half or possibly 3/4 of the cases based on an even odd parity thing to do with thinking about whether you can get through all of these things. Yeah, I like this. I think this is true. So then NCR minus Rn minus R. Yeah, something like this. Okay. You're trying to get all the eggs from here to, it's just an example, but over there. So I would say that's an egg that's moved 3, 3, 3. Oh, how many are there? R of them. 3, 3, 3, and they have moved n minus R each. So when you add that up for the parity or something, you can add them because it's parity with sum. It's going to be fine, yeah. R times n minus R or something. Maybe that's just how many steps it takes to get some sort of arithmetic progression, right? Oh, no, it's all of them moving forwards. How many steps? Yeah, okay. I would define parity first of a position. Okay, so you need NCR to have the same sign as n minus R times R, which doesn't happen all the time. Doesn't happen all the time, right? Almost. Yeah. Yeah, that feels like it rules out a lot of cases. That's impossible. And then your big power of 2 is something like, you've got Lucas's theorem as well. Good, right, okay, shall I look up Lucas's theorem? Is this going to be the one about primes dividing things? Oh my goodness. Oh gosh, okay. Yeah, I did not know Lucas's theorem at all. Fair enough. Right, good. I'm going to put it on the screen just because. Hooray! This? You're saying we should use this? Twitch chat. Surprisingly, on it with theorems that first appeared in the 19th century. What is going on? So then you've got this big power of 2 because you want to tell me that this, and you're looking more 2. Are you telling me they're all even? This is great fun. Where, right, base P expansions of MNN. So you've chosen it to have a very nice base P expansion, mod 2, so binary. I've never seen this theorem before in my life. This is crazy. Because then, if it's got a very simple binary expansion, with a 1 here and here for the thing you're trying to do in chat, then I just take the product of we 1 choose this and 1 choose that, which are both 1. This is odd or something. It's in a book I read. Cool. That's weird. I like it. I think I'm going to go and find out about it. Right, almost 4 o'clock, so I'm going to pause that. Ooh. Should turn off bookmarks. Oh, now I'm encouraging people to look at the bookmarks next time that's on screen. There's nothing incriminating in my bookmarks. But previously I got questions like, so I hide my bookmarks partly so that I don't accidentally click on them, and partly so that I don't get questions like, why do you have a bookmark labelled Cambridge? I hide my bookmarks, he says, pointing at them on stream. I think I'm sort of wrapping up a bit. I kind of want to learn Lucas's theorem. Or see where this is going. But this feels like it's stopping, right? Where's this going? Because we've just hit only partially understood. We've defined class number, but maybe this is going somewhere. Yeah, no, this is going in lots of places. Oh my goodness. There's about 3 or 4 pages of stuff that we can say. Still here. I'm going to read some of it, but in a very chill manner, if I can. Let's give that a go. Discriminants for which all forms are primitive. These are called fundamental discriminants. It's exciting. Does that just happen if... So suppose your discriminant... I know it's on screen, but suppose your discriminant doesn't have any square factors. What are you going to do now? Can't do anything non-primitive, right? Not a square times a smaller discriminant. Hooray! Square free. 8 is a fundamental discriminant, even though it's divisible by a square. Wait, what? It's not saying anything in square free? 2 is not the discriminant of any form. Oh, because it's not correlated to 0, 1 more 4. Oh my goodness. Technically 1, but we'll exclude this. Fundamental discriminants are never squares. Fundamental discriminants only appear for elliptic and hyperbolic forms. The fundamental discriminants less than 40 are... Wait, they're not just plus and minus themselves? What? But 5 but not minus 5. Oh, it is negative numbers. Yeah, negative numbers don't behave nicely under mod 4. Or don't behave the same, right? Minus 1 and 1 are not equivalent mod 4. So the rule about whether or not you can actually achieve these numbers with quadratic forms don't respect plus minus stuff. Well, this is weird. What am I saying? Oh, you can put a minus sign out in front of a quadratic form to change the values, but that doesn't flip the discriminants because b squared minus 4ac, well, it has. And b squared doesn't care if you change the sign of b, and 4ac doesn't care if you change the signs of both a and c. So getting discriminant -3 is really quite different from getting discriminant of 5. It's not a simple sign flip. And in particular, whether or not that's even possible for a quadratic form is not as simple as just sticking a minus sign out the front and calling it a day. Right. Okay, so these ones, not necessarily square free, but this is the thing about threes in... This is the thing about having... No. We've seen something before, right? Which numbers can you write as x squared plus y squared? There it is. Which numbers are the sum of two squares? And the answer turns out to be, after quite lots of maths, which I think might be coming up in our future, something to do with its prime factorisation. Something like the answer to that one was your prime factorisation can have as many 2's as you like. It can have a square factor, but then the non-square bit has to be only things that are 1 mod 4 as primes that are 1 mod 4. You can build those, like 5 is okay. 7's not okay. Is that what's going on here? I mean, not with the minus signs. And actually, no, that's not what's going on here at all. Yeah, there's something like that around here, isn't there? It smells the same, even though it's different. Right, okay. First, bring out all your factors of 2. Here you go, I've seen that before. N odd, possibly negative. If any odd square divides n, factor this out. Yep, good. Odd squares are congruent to 1 mod 4. Great. So we're not losing track of whether you're 0 or 1 or 1 mod 4. The exponent can never be 1. This would imply that you're 2 mod 4. Good. If k is more than 4, we can factor powers of 4 out of this, and you are 0 mod 4, right? Oh, until we have k equals 2 or 3. That's still discriminants. If k equals 3, we can't factor out 4, since that will give the excluded case k equals 1. So we're checking how many 2's you can have in your prime factorisation. If k equals 2, we can factor 4 is to get out of delta exactly when n is 1 mod 4. So we're looking at the prime left over bit. Finally, when k equals 0, we have delta is n. If you've got no 2's, you must have n to 1 mod 4. So in this case, you're okay. Product of distinct odd primes. These are fundamental. They don't admit. Yeah. You can't take a square out and still get something that you can make with a quadratic form. Gosh. We think you can make any of these numbers 1 mod 4 or 0 mod 4 because we've seen examples of how to do it. So if your quadratic form really had discriminant 12, then that includes some equivalence class where everything's a multiple of 2. Can't remember if we saw that or not. 12's impossible. Not 12. This is really hard. Because 12, you take out the factor of 4 and you get something that's 3 mod 4. No, that's what I want. Oh my goodness. What is that middle case, right? Discriminant 12 with n a product of discriminant odd primes and n is 3 mod 4. Yeah, okay, so 12. Right. We're getting there. So if your discriminant is odd, then don't worry about multiples of 2 at all. It's got to be 1 mod 4, because you can't make the ones that are 3 mod 4. And this is odd, so it's not going to be 0 mod 4. Your discriminant is always 0 or 1 mod 4. That bit makes sense to me. Okay, if it's not odd, if it's 2n but not 4n, then it's looking like it's 2 mod 4, so no. If it's 4n, then brilliant, okay. With n odd, then I'm still suspicious, right? Because I worry that you could take out this factor of 4, and if you can make something with n, if you can make something with n, then I'll do that. So you better make sure that n is actually 3 mod 4 as the other sort of odd number, so that I can't make it, because I'm looking for fundamental discriminants where you can't make something that's smaller a factor. Right, okay, and if the discriminant is 8n, then I'm worried about bringing out a factor of 4, but that would be then 2n, so actually don't have to worry about that, that'd be fine. You bring out a factor of 4, you get 2n. You can't make that, that's 2 mod 4. So don't worry about it. I am worried about n though. Am I worried about n? I suppose not. Ooh, someone started doing some DIY hammering. Maybe that's time to wrap up the stream. I'm worried about n because I'm a bit worried about n. What if you can't make n? Well, if you can't make n, then you can't make. I think you can make this one. I'm still worried you could bring out a factor of. Oh, the product of distinct odd primes, no square stuff. Yes, other odd squares we've said you could bring out and still have something that was 1 mod 4 afterwards if this was 1 mod 4 or 0 mod 4. So it'll be alright. Yeah, it actually stopped, yes. They are subscribed, of course. All of my neighbours are. And they do whatever chat says. That's how we've set it up around here. Not true. Right, okay, I'm still struggling with this one. We really don't care. As long as there aren't any squares in there for me to bring out, then you know, it could be 1 mod 4, it could be 3 mod 4, I don't mind. You're not going to make... Yeah, out anything goes. Feels like a trap, but I think we're alright. And then more than that, so if it's 16n, then I start pulling out a factor of 16. By 16 I can pull out a factor of 4 and still have something left that's still a multiple of 4, 0 mod 4, I can make that. Right, okay. Right, factored uniquely is this, where that's a fundamental discriminant. D is called the conductor. Conductors one. Become important when we study the deeper properties. But look in later chapters. This book is always telling us to read the next chapter. It's sort of cliffhangers all the way through. Class number is always a multiple. Ooh, for what this multiple is. So the determination reduces largely in the case of fundamental discriminants. We will not be going into more detail on the relationship in this book. Okay, sometimes the book lays on a cliffhanger for all of the rest of maths, which is the alternative, I suppose. Either read further chapters or just read anything else. If this has emboldened me to look up class number on Math World, because I think I'm aware of something else called class number. But possibly that's just a generic phrase that people use for lots of stuff. My goodness. Yeah, great. Maybe this is a bit much. Class numbers usually determine complex orders of number fields. Oh dear. Look at all these links I'd have to click on to understand what this is talking about. Yeah. Of a quadratic field. Oh, look, hello. It's equal to the number of reduced binary quadratic forms. Oh, it is this. I'd quite like to know this. The ring of integers. My goodness. Okay, so there's an associated ring of integers that I haven't grasped even slightly. If the number field this, crikey, it's equal to 3. So there are 3 reduced binary quadratic forms. Binary quadratic? Yes, binary quadratic forms of discriminant this. Saying binary because it's got 2 inputs, x and y. Like that. We've seen pictures of those today, I think. We could just count them to work out the class number. Ooh, sophisticated maths gives you these things involving sine. Can't wait for that. This is the fundamental unit. Let's click on that one just for fun. Oh, yuck. Ah, bro. I sort of like the way that this textbook is trying to teach us this just with diagrams and like, look at the picture and there are triangles everywhere, rather than, oh my goodness, all of this. Brill. Maths is so hard. So much. I've definitely seen this as Pinsky shape before for the egg problem. We definitely had a chart going at some point. I can't remember if it was computational or if it was a parity argument. We definitely had a cool Sierpinski triangle. No, we had a lattice shape, didn't we? Oh, well, I will go and think about it. Negated discriminants corresponding to the imaginary quadratic fields. Whoa. Odds 23, no. People have found big lists of these things or something, right? Is that what they're saying? Big lists. Okay, great. Here are some big lists. Oh, what a page. What are all of these? This is great. And this page has just got loads of numbers on it. Maths. Oh, there's 163. I've got a feeling that this is all going to be related to the fact that, what is it, e to the pi root minus 163? What's that fact? Let's see if we can work out that fact. There's like some amazing connection. We're never going to get there, but some amazing connection to the fact that, see if I can remember it, e to the minus 163 or something. It's like suspiciously close to an integer. One of these. Yeah, maybe this, maybe not. Not sure about this. Do I want pi in there as well? No. Not sure. What's the square root 163 fact? Let's try Googling it. Okay, welcome back to James Googles things. Pi but no I. Extremely. E to the pi root 163, says the internet. So it's this fact. Wait for it. I think this times 10 to the 17. Do I want more digits? I kind of want a decimal form. Right, where's the point? There's the point. So it's very close to being an integer. And it's followed by 9 and 9, 9 and 9, 9 and 9, 9 and 9. Which is weird because it is e to the pi root 163. And somebody told me once they'd been to some like really hard number theory courses or something, and they told me that the reason this happens is something like because there's a 163 in one of these class number tables, or there's some connection to fields of number fields. I have no idea. Right, good. Okay. Right, okay. I'm going to stop the stream there on that fact and say that next week we're going to be live at 4 o'clock instead of 2 o'clock UK time. So add 2 to whatever clock you were using for Chill Math streams. We will be live though. And we will do some more maths. Possibly, we're now exploring things that have important names. Whether or not we're going to understand them in a way, we're gonna go to interesting places. Class number 1 has been much studied. Hooray! So 5-pointed star here for where we're up to. The time change is at least 1 week. We're going to try it out. Possibly permanent. We will find out. I mean, is it a periodic function or is it just random now? Let's find out. See you next week. Have a good one. Yes. Oh yeah, we're just T changed to 5 o'clock. I guess T would be 3 o'clock, T o'clock would become 5 o'clock. T o'clock. It just doesn't rhyme. Oh no. We'll have to make up new law. Right, okay, I will see you next time. Have a good week. Bye. I'm ending the stream.